Hey guys, welcome to chapter that doesn't write well. 8.2 Calc 2. Alright, so last time we saw about arc length. I want you to imagine back to the day when we were doing revolutions that you have some function and we spin it around. Well, we end up with a volume of revolution. And we've calculated how to do this volume before. But now comes the question of what is the surface area? Now, if we want to use infinitesimal calculus, do things very on the small. Imagine we take and we cut this. We get that disk that we zoom out of there. And there's two ways to look at that hoop. One, as a box being revolved, and that surface area there. Another is kind of like a slanted hoop, and its surface area there. What we want to do is we want to calculate these two, and we want to figure out what's a good way for calculating the area, and then developing a formula for it. Well, there's a lot of simple techniques that we can apply. First, I'm going to tell you what the answer looks like. The surface area has a nice little formula. A is where it starts, and B is where this function ends. So we have an A to a B. And what we want to do is we want to somehow calculate a formula for surface area. Now, if I were telling you that this was 2 pi f of x times the square root of 1 plus f prime of x squared dx, you shouldn't be very surprised by what we're seeing. What we're seeing here is a 2 pi r, which very much looks like a circumference, and we're seeing also an arc length. What it looks like is that it's a cross between these. We have the length of the arc, and then we're spinning it around, and then we're adding all of these up. Let's just take a look at what this produces for us, because it's going to allow us to do some calculation that we may not have seen before. So let's start with a function that produces a fairly reasonable answer. We're going to start with f of x equals the square root of, let's say, 9 minus x squared. And we're going to do it on some interval from a to b. Now, this formula simply states that it's going to be the integral from a to b of 2 pi times the square root of 9 minus x squared, that's the f of x, times the square root of 1 plus, and now we need f prime of x, and we need to calculate that. So here we go. F prime of x will be 1/2 9 minus x squared, derivative of the 1/2 minus 1/2 power, times the derivative inside, a minus 2x. So we'll get f prime of x to be a minus x over 9 minus x squared to the 1/2. Now, we're going to put it square there. So the minus goes away, and we're going to get x squared over 9 minus x squared. And all done dx. Now, the algebra of putting that in there sounds, a little bit gross. But this problem, again, was like most of our surface area. Most of our arc lengths. It was designed to make our life actually easy. And you notice that when I got a common denominator, this cancels. Square it in the bottom, square it in the top. This cancels. It comes down to 2 pi times 3, the integral from a to b dx. And so this is 2 pi times 3, x evaluated from a to b. So our final answer is 6 pi b minus a. That's a pretty straightforward, simple calculation. And what is surprising here is that even though this looked hard, it simplified fairly radically. So we do have to be a little careful when we do these integrals, and we have to hope that in some cases they work out nicely. Now, I don't know if any of you have ever seen the area of a sphere derived. So I'm going to completely derive the area of a sphere. Now, it takes a little bit of time because the integral is going to be nasty. We got to make sure we set it up correctly, and we got to make sure that we don't double count anything. So here we go. I'm going to start with the function defined implicitly that x squared plus y squared equals r squared. Now that's a circle of radius r. Now I'd like to spin this around, so I want to throw away the bottom half, spin this around, and then calculate again. So here we go. So I'm going to start by solving for this function f. So y squared is equal to r squared minus x squared. So y is plus or minus the square root of r squared minus x squared. Now, if we want the top half, we're going to throw away the minus. So now we have our function, f of x, which is the positive value, the square root of r squared minus x squared. Now, it's 0 at minus r to r. And so there's our range that we're going to let x vary over. And now we're going to plug in the surface area formula. Now as this spins around, the integral from minus r to r of 2 pi square root of r squared minus x squared times the square root. Now this was exactly the form of the previous problem that we worked on. So it is 1 plus, and this thing is squared, so we have a minus x over r squared minus x squared square root squared. You can check it by doing the derivative. And so we're going to get minus r to r of 2 pi, the square root of r squared minus x squared. Now, r squared minus x squared over r squared minus x squared will cancel the x squared. We'll get the square root of r squared over the square root of r squared minus x squared. This cancels dx. And so we're going to get 2 pi r integral from minus r to r dx. We're going to get 2 pi r x evaluated from minus r to r. And we're going to get 2 pi r squared minus 2 pi r squared. We're going to get 4 pi r squared. We now happen to know the surface area of a sphere. By the way, we calculated the volume of a sphere much earlier. It was 4/3 pi r cubed. I'd like you to notice that this formula is a rather nice one to remember. The surface area looks like the derivative of it. It looks like 4 pi r squared. Now, one would think if that happened, you can take another derivative and get the circumference, and you actually get 8 pi r, and we happen to know that the circumference of a circle is 2 pi r. It's like we got way too many multiples. So it's just a mnemonic aid to help you remember. All right,